Okay. So I think you people are appearing for the test, like in some a week in time, or when is your test? So are you appearing for the test, Ranjit?
Yes, test is on coming Monday,
Okay.
and I'm preparing for that test.
Uh,
And if you give me some suggestions regarding
yeah.
test, it will be very helpful for me. Thank you.
Okay, okay, yeah, yeah. It is. You don't have to worry a lot about the test. Like it's just going to be the exercises that you have seen all these lectures. I mean, particularly the assignments. I think you have gone through them well. So that is the key thing. So you go through assignments problems once again. Pretty much uh, I mean everything that covers. So because that is the type of questions that you can expect, and and yeah, and also there won't be any particular question that could come out of the topic which has not been talked about, which has not been even discussed in any way. So there's I mean it won't be very difficult. It is going to be like if you have familiar you I mean if you have familiar with the assignment problems already, covering I mean all the weeks which starting from week 1 to week 8, then it is going to be not tough for you. Like you can do that. I mean this is not going to be tough in any way, so it would be good. So and also also in problem solving session also, like you can see, like I think the transcript I mean the problem solving notes are also uploaded in somewhere in your NPTEL portal. You can get that. So there are also some problems, worked out problems. You can look out there, like how the problems are solved. And again those problems are also relevant, like particularly the problems which I have discussed here in all the sessions of I mean every week of your I mean in every week of your NPTEL course. This course, I have talked about some particular relevant problems relating to that week's assignment. So like you can go and check them out once it possible. So like because and also I think solutions are some of the solutions are also shared with you, so you can also verify how the questions have been solved. So nothing to worry a lot about it, but it's going to be straightforward, like if you just practice the assignment problems. And yeah. And do you have any other particular doubt or something? Yeah. Any particular doubt, like you can tell right here. So there's nothing no such question you would expect, like the coming out of the topic which has not been even discussed right here in this course. So like this is already like a 8 week course, like ample amount of topics have been covered. So so if there's any particular doubt, we can discuss right here, or any kind of problem. If not, like we can move on with something bit more extra topic that we missed out during this problem solving session. So like I was talking about Bell's inequality, and also there was a doubt in time dependent perturbation or some interaction pictures we will also talk about. So yeah. And something more, if you have to say, like you can tell me right now. If not, if you want to tell at the end also, that is also fine. Or like, uh, so
Hello,
yeah, yeah,
hello,
yeah,
hello.
yeah. I
Can you
can hear
hear
you.
me?
Yeah, yeah, I can hear you. I can go on.
Um, if you please discuss about the interaction pictures and also about the density matrix and coherent states.
Density metrics and coherent states. Okay, so like okay, then I can talk about them, density states and coherent states, but
D- d-
like
density matrix and maybe something about symmetries.
something about symmetries in the sense like what kind of symmetry, like you mean discrete symmetries like parity, charge conservation, these things, time reversal symmetry.
Parity and transform, parity, time reversal and and these three.
Okay, okay, like like I will try to talk about them,
If
but
you have time,
yeah, yeah,
it's not
because
necessary, but if you have time.
yeah, yeah, yeah. Like since I think you are the one you told me about interaction picture, so like I have planned to
Yes,
discuss.
yes.
I have also made a certain note about things like which we will discuss, and also along with it, like as I also said, like I missed out the like this proof on Bell inequality and on this peer thing. So we'll also talk briefly about it. So if possible, I will talk about them like coherent states and density matrices, like symmetries. Those are a lot of things. So like we'll try. Like I mean, if possible, we can. I will talk
Okay,
about
okay, okay.
it. So, yeah, like those are important things. Like of course,
Okay.
what the topics you said, we should know that. Like one has to know those things very well. So, but we'll see. Like if possible, like we can talk about that. Sure. So, okay, like maybe we can start discuss about this Bell's inequality. So, uh, okay. So, like, what is Bell's inequality? This is like something like one of the like a famous physicist John Bell came about with. So, why like he proposed this this inequality, like what is up to this particularly. So, so what happened, like after I mean the like after when quantum mechanics was flourishing around the beginning of 20th century. So many new theories were coming up, like I mean in succession. But during that time, like there were few people like who had some concern about the theories. I mean the completeness of the theory. So it was particularly Einstein, Podolsky, Rosen. So. So like famously we also know by as EPR. So um, so like uh, so they uh, they came about with a paper which highlighting some like I mean some features of quantum mechanics which they found it uh, clashing with the old principles of physics, or like they had some conflicting issues which has been like which was basically highlighted by EPR, and that is what something we know with it as EPR paradox. So, like if you remember, like we can start this by looking into this entangled state, which is denoted as psi. So, like if you remember, like we like discussed a lot about this thing. Like I mean, we talked about some quantum key distributions and teleportation, dense coding, all these things. Like in one of our like I think previous week session. I think it would be week 5 or 6. I think maybe week 5. So so we talked about this entangled state a lot, so which we often also I mean denoted as something uh, as EPR state. So so this is like maximally entangled state. So, so now, what is like EPR paradox? What Einstein, Podolsky, Rosen claim. So, so they I mean, Einstein-Podolsky-Rosen claimed that quantum mechanics is incomplete. Incomplete in the sense like like the various notions of quantum mechanics, like particularly the probabilistic notion of quantum mechanics, like how like it is really incomprehensible to understand in a way like how classical physics works. So quantum mechanics doesn't work classical with classical intuitions. So it is something we go with the interpretive. I think you know, or you at least heard about Copenhagen interpretation. So that is the interpretation which we see like the instantaneous collapse of wave function, which means particularly like for example if we if we know a quantum state, that is what like let's say there is a quantum system, and you want to measure the state of the system, and upon your measurement your basically the quantum system which was initially in some superposition before your measurement, and after when you do the measurement it it collapses to some particular eigenstate, some state. So that notion is something which Einstein Podolsky Rosen felt incomplete, particularly if you see the entangled state. So EPR, this EPR state, if you see, this is a entangled of two spin-off particles. So like you can think of any entangled system. Like for example, there exists many lot of entangled system of spin-offs. Like for example, if you see photons, or if you see qubits, or even what uh, your like for example in particle physics you see this muon decay. So in muon decay also you see I mean two muon particles would be entangled, where basically one would be having some positive spin, and other having negative spin, or or in other words, if one is in spinning upwards and other would be spinning downwards. So that is the notion that we know. So what happens if they are entangled, so if you measure one of the spin of one muon particle, then all of a sudden instantaneously you also get to know the spin of the other half, or the other entangled pair, or the other muon particle. So that is something which doesn't really fit into the classical notion, like how this can happen. So like they said like Einstein Podolsky Rosen, like they said if the instantaneous collapse of wave function, for example in entangled state, would really occurs in nature, then that has to something do with or it must conflict with special relativity. So special relativity says instantaneously something cannot go through. We also know if any signal has to pass through, let's say if the signal has to be in the form of electromagnetic form, then even there the information has to travel instantaneously, but which is not possible because we know the faster which anything which goes, it is the speed of light, and beyond which is nothing allowed. That is we know by the special relativity. So yeah, so that is it felt that even special relativity is getting violated in some way right here in this picture of instantaneous collapse of wave function. So they said there can be something more which we call it as hidden variable theory. So they proposed the idea of hidden variable theory, which said that there can be something more happening, so that this basic postulates or principles of special relativity and in physics in general are not violated when we are trying to explain this notion of quantum mechanics. So they said there is something more happening. Like for example, if you think of let's say this entangled state as let's say pair of shoes. So if I have let's say if I have pair of shoes which has left pair and the right one. So and let's say if I put this left shoe in one of the box, let's say in box 1, and right shoe in the box 2. So, and if I shuffle them up, and if I give it to two different person, let's say they are Alice and Bob. So I gave Alice the box 1 and box 2 to Bob. So then, like, if I would ask Bob to reveal which pair of the shoes you have got in your suitcase or in your box, then he would reveal that I have the right one. Then instantaneously we get to know that Alice eventually has the left pair of the shoe. So I mean, you'd see there is nothing instantaneously collapsing right when Bob measured his box, that is box 2. So he found out that he has the right pair. He's the right pair of the shoe. So then it is not something happening that right at the point when Bob measured, and Alice is getting to know that, or right at the point when Bob measured, that Alice's shoe suddenly collapsing to something left pair of shoe. It was already there with Alice. I mean, her left pair of shoe, and with Bob his right pair of shoe. So they already have the. I mean, right from the starting, they already had left and right from the beginning. The only thing was they didn't knew which pair of the shoe was they were carrying. So they only came to know upon measuring, or let's say they only came to know upon one measurement, because you can understand whether Alice measures her box or Bob measures his box. They eventually they will get to know which pair of shoe who is carrying, because if one measures, then eventually the other gets to know, yeah, what would be the, or even if Alice measures her box, then she get to know that she is carrying the left pair, and eventually Bob is getting to know that Bob will surely carry the right pair of shoe. So that is something even Einstein Podolsky Rosen claimed that that should also go for the quantum entanglement case, because as I said, if there are two muon particles, if they are entangled, then you know that, yeah, I mean, if one muon has the positive spin and the other muon has the negative spin, then it also has to be, the spins are also assigned right from the moment when they were separated. So they were already having that, but we are only getting to know that which spin that one of the muon particle is having when we do the measurement. But and why we are unable to know why which spin which muon particle is carrying right from the beginning, it is because we are incapable of some information, or accessing some information, or some informations are missed out from our worldview, or something which we are incapable to understand what is going around it, but those information are stored in some hidden variables, or they are encoded in some hidden variable information which we are unable to access. So it is our due to on ignorance we are unable to know which spin which particle is carrying, and we are only able to getting to know that after the measurement. So that is the argument which APR posed on this quantum entanglement issue, because that is how you can escape that instantaneous collapse of wave function, which would prevent violation of special relativity postulate. So that is one of the way that Einstein-Podolsky Rosen came about to say that there can be hidden variables which we are not familiar with. Because of hidden variables, we can say that the entanglement which we know, the positive spin and the negative spin, they are already there, but we are only able to know when we are doing the measurement. they are already like we can we could have known that right from the start, like which particle is having which spin, if we have access to this hidden variable. So, like the example which I said for the pair of shoes, we know like the left pair and right pair of shoe was already there right from the beginning. They were not in some superposition. The left and right pair shoe were like was not in like some kind of superposition in box one, neither in box two. It was already some separated left shoe and right shoe was already there. So we are only getting to know when we are doing the measurement. So yeah, so so in order to see like how hidden variable theory in order to check do hidden variable theories exist around us or not, uh, John Bell came about with a mathematical proof which like he would prove it through a inequality equation, which we'll see that like we'll understand how that happens, and from that it will settle the argument like whether hidden variable theory is like one of the like necessary thing we have, like we need to necessary thing to understand quantum mechanics, or something quantum mechanics is already like uh, like uh, compatible or already right from whatever the arguments that we know, like, or if it is right, then how like it is like like preserving, or how it is like solving this paradox. So to understand that, like we'll start with the entangled state again. So now if you would see like I'm writing this entangled state in this you see the up arrow and down arrow represents the upspin and upspin of particle, and uh, and also this upspin downspin are the eigenstates of sz operator. Like you if you are like I think you know like in spin-up particles, like we have talked about this a lot in one of previous week, that I mean we have talked about a lot in many weeks, that this these are the eigenstates for like the eigenstates of Sz. So similarly, you can write the eigenstates you can write the eigenstates of Ss of Sx as these are the eigenstates of Sx. So this is a relation which you can write. Let's say this right arrow represents the first eigenstate of the Sx operator. So that you can write it as like the sum of two eigenstates of Sz with a square root of 1 by root 2. So like if you would know, like we had Sz as some like h bar by 2 sigma z was something like 100 minus 1, like it had two eigenstates 1001. This we denoted as up spin, and this we denoted as down spin. Similarly, like we also had like sx h bar by 2 and sigma x. So and this was represented by something 0110. So and here in this case you had eigenstates like 1 1 and 1 minus 1. So yeah, with the square root 1 by 2 factor. So you can see like you can establish uh, so this we are representing this as this. So you can see we can establish relation between these two eigenstates and these two eigenstates. So that is what this the relation is given by. So right arrow is given by this, and left arrow is given by the difference of the eigenstate of sz, that is up arrow minus down arrow with the overall 1 over square root 2 factor. So yeah, so in that basis, so we can write our entangled state as some like we can you can see you can substitute what is up arrow in terms of left and right arrow. So this is right and left arrow. So you can substitute all the up and down arrow in this EPS table in terms of left and right arrow. So that will give you this. So like you can check that it can like this is what you will have your EPS state in terms of left and right. So this is EPS state in SX basis along. So if you are doing measurement along like x-axis, so this is the EPR you will get. I mean, in terms of left and right. And suppose if you are measuring like spin along any arbitrary direction, along some arbitrary direction a, that is a vector is given in sine theta like I cap and cos theta z cap. So like let's say that vector is some x in xz plane making theta angle with the z axis um, and yeah, theta angle with the like j axis and like some 90 minus theta with the x axis. Then you will see that like your you can write that vector, or basically this is sigma dot a, sigma dot a, that means like you can write it as sigma x a1 plus sigma y a2 plus sigma z a3. So let's say call this one as a1 and this is 0 a2 and this is a3. So and sigma is sigma, y is sigma z are Pauli matrices. Like for example, this I showed you right here. So this is sigma z and sigma x. This is, and similarly you have sigma y. So you write this uh, I mean so if you write this dot product, like this is what your the resultant matrix you will get. And if you take the eigenvector of this matrix, you will have if you would compute the eigenvector, this is the eigenvector you will get. You can check that out. So again, so now like for this like for this case, like even theta plus theta minus, so these are the eigenstate for this like if you check out some other like textbook, like some standard textbook, they would take a even more like a generic vector along the space. So where you also have some like phi some we have taken this vector in x step. Let's say if I would have taken something more arbitrary, not in x step, some like in maybe lying in outside of x step plane. So in that case, like I would have something phi also here. So now let's say that phi is not taken here to simplify things, but in that case also you will have this eigenvector theta plus and theta minus, where you would also additionally you would also have some ei phi by 2 or something. Here you have e minus I phi 2. So you can check that, like maybe like in Griffith or some standard textbook, like it would be there here. So yeah, so for the vector that we have chosen, you're in the x separate, and in that, like you will have this theta plus and theta minus. So yeah, and again you can write your EPR, your entangled state in terms of theta plus and theta minus. As we write, as we wrote our EPR state in terms of right arrow, left arrow. That was EPR state in terms of SX basis in when we are doing measurement along x-axis. And now like when we are doing measurement along some vector a along that direction, so we will write the EPR in its respective basis, that is theta plus and theta minus. So that will come out to be as this thing. So in all this thing, like you will see, like if you are if one is measuring theta plus, then like let's say if this 1/√2 theta plus theta minus, this state represents an entangled state for two particles which are entangled together, and those two entangled pairs are distributed among Alice and Bob. So you will see that if Alice Bob, if Alice's measurement is giving theta plus, then eventually Bob would get theta minus. So same with here also. So these are all entangled states. Like the same entangled state, I'm writing on a different basis. That's it. So now suppose if I initially have the state something is down arrow, that is SG basis, like in the jet direction. So what would happen, like if I measure like what is the probability that like my measurement initially it was in the down state, and let's say after some time I'm trying to measure what is like what I mean what is the probability that I would get that s theta plus. Then what you will do, so this probability actually means initially uh, I had this state down state, so that I will write this one and theta plus. So so this is what like it means. So if you see, like if I do a inner product of down state with theta plus, so like here if you do, I mean if you would write right inner product, like if you take the inner product by taking the graph down arrow, so you will see that like you will get sine theta by 2. And since you know this down arrow up arrow are orthonormal bases, I mean they would like down arrow like up arrow basically orthogonal. So you will only get the contribution from the second term, that is sine theta over 2. And if you take the inner product square, that gives you the probability, that is sine square theta by 2. So yeah, so that is like how you get the probability, like initially if you would have downstream. And same way, like what is the probability if you get like initially if you have down arrow, and what is the probability of getting that down arrow to be in theta minus 10. That is this one right here. So in theta minus, again you will do the same thing. You like take the inner product. So then you will yeah, then you will get this cost method. So now like what happens, suppose we are doing we are doing an exercise to check how all these things works, and in presence of hidden variable theory, like what would happen. Suppose if Alice, we are doing an exercise where Alice is measuring the entangled pair. So Alice is having one of the entangled pair and Bob is having another entangled pair. So Alice is measuring her entangled pair along z-axis, and Bob is measuring his entangled pair along the arbitrary a axis, which is an x segment. So then if you would calculate what is the probability that let's say what is the probability that this notation basically means P of sigma z a plus. That means uh, Alice is measuring along z axis, and her measurement came out to be plus. That means uh, measurement like basically uh, uh, I mean what I mean to say, sigma z a, if that is plus, that means uh, the measurement of Alice on her entangled pair like along z direction gave this state. So this is the outcome of the state when Alice measured. So uh, and when Bob is measuring, and if he is getting clustered, that means what is the probability that I mean his measurement basically like yield theta plus step. So, so what is the probability that that when Alice measures her entangled pair, and she is getting this upstate, what is the probability of getting this upstate? So if you see like the entangled pair, then that there is 50-50 chance. So you will see that like probability of getting. So this means probability of getting. Probability of sigma is at a equal to plus uh, uh, multiplied with probability of uh, sigma theta b equal to plus. So initially when Alice is measuring, so Alice is like starting the measurement. So when she's doing the measurement, and if she's getting plus state, that means the up arrow state, then what is the probability of getting that state? that will be 1 by 2, because the entire state has like 50-50 chance of getting upstate or downstate. So yeah, so when now Alice measured her spin, and let's say and she got the upstate. So if she's getting the upstate, then we know from quantum entanglement that the bob will also the I mean the bob state will collapses to down state. So now Bob has this state along z basis, but you remember the Bob is measuring along theta direction, along or along a axis, that is in theta basis. So we have to calculate what is probability of sigma theta b equal to plus. That means what is the probability of getting theta plus for Bob. So that means like Bob has to take this probability, like this has to be like multiplied uh, down arrow with theta plus the one which yeah, this one right here. Why? Because like after when Alice's measurement, so like her measurement is giving, if her measurement is giving like upstate, then it has to be downstate for Bob, because that measurement like collapses the state, like whichever theory I mean whichever like theory you believe, like the quantum entanglement as proposed initially, or the quantum entanglement with hidden variables. In either way, like you know that like I mean if you have a like a one entangled state, and upon measurement if you are getting to know what is the exact state, then the like the counterpart would be the for the other particle state. So if Alice is measuring along z direction and she is getting upstate, then Bob has to get downstate along z direction, that is down arrow. So initially Bob had downstate, but Bob is measuring along theta plus along a axis, that is theta plus basis. So Bob has to take Bob has to estimate what is this probability. I mean, what is the value of this? Because Bob is getting theta plus, and as he is measuring along a axis, so the probability would be like inner product of this downstar with theta plus. So that will give half sine square theta by 2. And same way, like you have also other cases, like in this case also you can say that like uh, half for again L is getting plus state, that is upstate, and then uh, uh, like Bob is getting minus, that means theta minus state, so that means this is this probability. So this will give you half cos square theta. And same way, like for I mean for this case you will have um, a half L is getting downstairs, 50-50 chance, so that means half chance of getting downstairs. And again, if L is getting downstairs, that means Bob will get upstairs, and that inner product with theta plus, like because theta plus is the outcome what Bob is getting, then this is the probability you get half cos square theta by 2. So same way, like if you like go on to calculate, these are the things that you will get. So yeah, so yeah, these are the like possible outcomes you can have. Now suppose like if we will do what like uh, just a minute. Yeah, so these are the results that you have. I mean the probabilities that you have upon like simultaneous measurement of Alice and Bob, or not simultaneous. I mean after the the exercise of like measurement process, where Alice is first measuring along z-axis, and then Bob is measuring along a-axis. So that is the result here. Now suppose like we say that like these measurements are already like prefixed, or basically not prefixed, I would say like already they are determined through some hidden variables. Let's say, like as I said, um, I mean, the collapse of state when Alice is measuring and her state is coming out to be upstate, and right at that instant, like we say that like Bob is getting the downstate along Z direction. Let's say that like it was already there right from the beginning. Alice already was getting like upstate with her, and Bob was getting downstate with him, and that is happening through some like this hidden variables which we do not have any idea before the measurement. So let's say that it was already there before. So what would happen? So now we'll say, I mean, uh, like like the this anti-correlation, I mean, for Pop's particle, will always carry the opposite spin of Alice particle, so that we can write it as, let's say, along Z direction, whatever the result Bob would have, that would be the negative of Alice result. Same, what would be the result of Bob would have along theta direction, or that is a axis, then Alice would have the opposite of it or negative of it. Like, so these are anti-correlation relation. So like these are we saying we are this will already be there, not at the point of measurement. This is already will be there right from the beginning according to hidden variable theory. Like the example as I said to by taking analogy of a pair of shoes. So yeah, so left and right shoe, that axis anti-correlation. So, so in this case, like if you would calculate these probabilities again, like what you will get. So let's say I'm, let's say I'm going with this same probabilities right again right here. So let's call this A, B. So for case A, we have probability of sigma z a, so that let's say I'm denoting sz this time, sz a, s plus. And so now you see, if this is sigma theta b equal to plus, that means like classically according to hidden variables, that means sigma theta b is plus, that means sigma theta a is minus according to this relation. So I can write it as s theta uh, a equal to minus equal to, you will have this probability. So same way, like if I write set a equal to plus, and uh, for b is measurement. Uh, so in this case, like sigma theta is b, that means s theta a is minus, that is half cos square theta by 2. And same way, if I do uh, p of uh, s j a equal to minus, that means uh, s theta a is minus, that is half cos square theta by 2. uh, and s z a equal to minus, s theta a equal to plus, then that will give me half sin square theta by 2. So now you see right here, like yeah, I mean, you will see this. These are the probabilities that we will have corresponding to each measurements which we did without any like assumption of hidden variables or any pre-assumption of that that spins are anti-correlated from the beginning. So those results were this, and I mean those were these results. But now, like when we assume this anti-correlation right from the beginning, so we have these properties. Now you see, like for example, like in each of these cases, we are getting probability of sz a to be plus and s theta a to be minus, and that itself is clearly hinting something wrong here. I mean, at least if we at least if we think about quantum mechanics, what happens like if I'm saying that I'm getting a plus state along the measurement on z direction and minus state along the measurement along theta or a direction, that is s theta a, that means like I'm simultaneously doing the measurement, I'm getting some probability which is not possible because like you should know that this very well that like I mean in quantum mechanics this spin axis or the spin operators like SZ like or S theta or whatever S phi or uh, SX, they all do not, I mean they do not like commute with each other. So these operators like you cannot measure simultaneously I mean you cannot simultaneously measure their results, I mean like because they do not share a common eigenstates, they have their own unique eigenstates, their eigenstates are different from one another. So like as we see already before that, because we are denoting up and down state for G SZ operator and left and right arrow for the SX operator. So you can understand that this is something uh, going wrong in some, so it is already heading forward with some problem. So let's see what happens moving on. But something which you cannot write here, like I mean, you are doing measurement like simultaneously in two different measurement, or simultaneously you are measuring two operators which basically they do not commute, so you can only measure two operators simultaneously if they commute with each other. So that is what we know in quantum mechanics. um, so let's say I mean uh, as I was telling, like if suppose if we introduce another axis, like I mean, uh, we know that we were so far we had a vector that was I was denoting with sine theta 0 cos theta. Suppose if I would have taken some another, so along this axis we were measuring what would be the state, like we found out like we would have theta plus theta minus state. So that is what we were denoting, that is s theta a and s theta b, so on. So let's say if we introduce another axis of measurement, that is denoted with b as sine phi and 0 cos phi. So uh, like in the same let's say in the same xz plane, but with some phi angle, not with theta angle, where the vector and z axis we are making. So now you have cos phi and sin phi. So like in this case, you will again have some outcomes in form of sz a s s theta a and s phi a. So you will see that again you can correspondingly you can calculate probabilities, that the probabilities of getting all the measurements of these three operators to be something plus minus whatever, like you can correspondingly calculate, you will get some probability expression. So again this is not possible in quantum mechanics. So let's say now like if we um, uh, like if I write a probability relation in the form uh, probability of s theta a to be plus and probability of s phi a to be minus, then I can write that as um, um, probability of what probability of uh, plus minus, or let me write in this way, that is s shared a equal to plus s theta a equal to plus and s phi a equal to minus plus s at a equal to minus s theta a equal to plus and s5 a equal to minus. So that means I can not better simplified notation, but I will just simply write this. So I can write this probability expression further. Like what I can also write, you will see that I mean in this relation I can write it as less than or equal to if I add uh, p plus minus p plus plus p plus b minus. So additionally, I added uh, two more terms here. So that's why like your RHS would become higher, like would become bigger compared to your LHS. Or in any case, if these two probabilities are zero, then they would be basically equal to your LHS as it was before. So that's why like I am writing this less than or equal to. So now, if I would if I would do them up, so then it would become P of S theta A equal to plus S phi A equal to minus less than equal to P of S z equal to S z A equal to plus S theta A equal to plus P of S z A equal to minus S phi A equal to minus. So this is the inequality relation which I will learn. So this is what we call as like Bell inequality. So yeah. So and now, like if you would calculate the probability and if you write the, um, I mean, like in terms of, the actual expression, or like I would write this is sine square theta minus 5/2, then less than equal to cos square theta by 2 plus cos square pi by 2. So these are the probability expression which you will have for cos square pi by 2 for this probability cos square theta by 2 for this probability and sine square theta minus pi by 2 for this probability. So you can calculate this as similarly like we like how we computed the probabilities before in the above expressions. Like, same way you can find out. So yeah, this is the actual in terms of explicit expression. Like of probabilities, this is the Venn inequality. Now suppose that if uh, uh, mm, let's say like if we check this inequality, like do this. I mean, is this inequality really true, or it has any problem? Suppose if you let's say. Uh, uh, Take theta equals to pi over 3 pi over 2, theta equals to 3 pi over 2, and phi equals to 3 pi over 4. In this case, what you have, if you calculate uh, uh, yeah, s- uh, sine square 3 pi over 4, yeah, sine square 3 pi uh, 8 minus cos square 3 pi 8 will basically give you minus cos 3 pi over 4, that is 1 over root 2. So yeah, that is Uh, uh, yeah, if I only write the cos squared 3 pi over 4, uh, so that is basically uh, 1 over 2. So now, like, if you check this out, like, I mean, uh, like, yeah, like, you see here, like, now this, like, 1 by 2, like, if you like put this in the inequality, like, you will find out this 1 by 2 will come out to be as 1 over square root 2, like, which isn't the case. uh, but I mean, this is this is like, you can see the inequality which with which has been we derived this thing, like, do not come out to be like the actual inequality. Listen, so this inequality actually doesn't hold true. So so you see that, like, for this particular angle, it is violating the Bell's inequality. So you can say, like, the hidden variable assumption that we made out earlier, like, this assumption will not work here, because hidden variable assumption only, like, giving us the idea that like, everything is already predetermined, but due to some like possibility, or due to some incapability of our measurement, or due to some ignorance, we are not getting like those I mean those state initially. I mean, what I mean to say, that plus state and down state, the plus and minus state, was already there right before the measurement. So it is not, there is no instantaneous collapse. So that is what this hidden variable theory proposed. um, so, like, first of all, like, are you, like, getting this, no, proof, or, like, did you get, or any problem in understanding? You can tell. Anything, any problem, or are you getting anything? Hello.
It's okay. Okay.
Yeah, yeah. Clear is
Yes, yes.
okay. So yeah, so this is how.
Actually, the
Hmm. Yeah.
actually I missed something because of network connection, but it is okay. I will see it later. It's okay.
Oh, right. So, like, where exactly?
Hello.
Like, what happened? Like, you missed something. Like, where exactly?
I missed something because of the internet connections. It
Okay,
is
okay.
my fault actually. So
Yeah,
I
yeah,
will check it again. Okay. 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 Thank you.
yeah. I mean, if you have any problem, like, if you missed out something here, like, I can tell you right here immediately. There's no problem.
It's okay. It's okay.
Okay, so yeah, so this is what I was telling. So, like, I mean, uh, like, this is what how the inequality, like, violates if you assume hidden variables. Like, I mean, like, this hidden variable also, like, you can understand, like, this or to, like, if you would understand this with another example, if I would give, let's suppose that if I, ask you for like an exercise of tossing a coin. So, like, when you toss a coin, so there are two outcomes, like, head and tail for a unbiased coin. So let's say, if I, like, before tossing the coin, like, I would ask you, like, what would be the outcome of the result. So you would tell the result with some 50% certainty, that, like, there would be 50% chance that it would come out to be head, and 50% chance that it will come out to be tail. But like, at the same time, like, if I would tell you that, like, it is also possible that to tell you, like, to when you toss a coin, the outcome would be either head or tail with 100% certainty. I mean, it may seem little weird or strange. I mean, how this is possible, but it is. I mean, for example, if you would assume as some, or if you think of as some, if you have the all the capability, you have all the facility. Let's say, if you have some. super computing devices around you, such that what happens when you when you try to toss a coin, so like you capture all the information, what is the conditions, or what are the possible ways that you are tossing a coin, and you are recording them everything. Let's say if you are tossing a coin with a uh, head faced I mean with the head facing towards you, and the tail facing towards your, I mean, on your finger, and then you are measuring and you are tossing the coin. I mean, when you are tossing the coin, you are tossing it with some torque. You are giving some torque on the coin so that it is flipping and moving upwards, and also you are giving with some torque. You are also giving some linear force, and then you will also measure what is the air resistance to the torque. What is the air resistance to the coin? Yeah, that torque which you given to the coin, and also you will measure what is the exact value of acceleration due to gravity around that region where you are tossing the coin, and you will measure after when it falls on the ground, then it will basically bounce back. So you also measure what is the elasticity of the ground that you are in when you are doing this exercise, and you will measure all the things like coefficient of residues and all these things that you know. So let's say you are able to record this through some supercomputing device. You can get all the information. Then you can with certainty you will say that like your outcome would be either head or tail, because you have recorded everything there can be. And all this information which you have recorded through some supercomputing devices, that is what Einstein Podolsky Rosen is calling out as hidden variables, or hidden variable information, because that is something we are incapable to know, because of which we say that we are uncertain of the result. But that is already encoded in some form which we are unable to, or we are access it. So that is what hidden variables. But what we got from uh, the Bell's inequality theorem, that quantum mechanical probabilities are also not just that. They are very different. Like it's not like they are already predetermined, because what we saw from this exercise, that Bell's inequality, which is violating right here, they work very differently. The instantaneous scholars still that explanation holds value in various contexts, and thus hidden variable theory you cannot bring there. And also the idea of, I mean, that paradox which I mean post the argument on the postulate of special relativity, which said that like it can violate the special relativity principle, which is not exact. If you see, let's say if Alice is positive, measuring the the her entanglement pair, which is coming out to be upward spin, which is coming out to be plus spin, then Bob will also get the downspin. But there is no something going around. It's I mean, when Alice is doing the measurement, let's say like Alice and Bob are doing this measurement on their entangled pair, where they are separated like miles away, very like they are separated by some galaxies. So if Alice is measuring the her entanglement pair, which is coming out to be plus, then we are saying instantaneously Bob is getting the minus two. But it is not. Bob will only get to know when Bob measures his entanglement pair. So until that, like Bob is also not aware of what is the outcome of the state. So it is not like the information has been transmitted like from million miles from one region to other another region from which are million miles away in in some split of second. So that is not possible. That is not happening right here. Nothing sort of that happening here. Bob will only get to know when Bob measures. So there is no transmission of signal that we initially thought about. So if you say that people also said like there are some something to do with locality, and locality could be violated here, but still again, so this is apparently a non-local phenomenon, like this entanglement, which they are not transmitting anything to each other, like that is the state which has been like collapsed upon the measurement, like you will see that like the other person can only get to know if he or she does the measurement, and it is sure to the previous person that the outcome will be the anti-correlated one when the second person will measure it. So that is that I mean Penn inequality, which settled the argument of the hidden variable theory could be a possible explanation for the comprehensive to comprehensively deal the understanding of quantum mechanics. So so I hope this is clear, like, or something more to say, like I can tell you. This is clear.
Yes, yes.
Okay. So yeah, so then like we can talk about interaction picture. So like if you remember, like I have talked about this interaction picture like in one of the previous week, I think in week uh, 4, I guess. So in week 4, like so like there was a problem on this time dependent perturbation. So in order to solve that, like I have to go to this interaction picture and solve it. So maybe during that time I explicitly did introduce this, I mean, interaction picture, and then solve the question properly there, because like I immediately went to the problem. So maybe I can review this interaction picture a bit more, and we can see that problem once again, like how that was solved out. So yeah, so what happens in interaction picture? So before like going to interaction picture, there is a little bit of overview of what we know in quantum mechanics in Schrodinger picture. That is what happens in Schrodinger picture. So uh, we have some like time independent Hamiltonian H naught, and uh, yeah, we have some time independent Hamiltonian H naught, and then like if you want to like evolve this Hamiltonian, sorry, if you want to evolve the system that you are having, like it would have some initial state that we are calling it as psi of t equals to 0 at t equals to 0, and you want to evolve it, then you use this evolution operator, that is exponential of minus I h naught or h bar t. So that is the this is the evolution of like your state, like, time evolution of psi. So and then if your state, like your psi of t0, like that is initial state, if it is expressed in some kind of linear combination of eigenstate of the Hamiltonian, then this is the like phi n are the eigenstate of Hamiltonian h naught, that is which is time independent Hamiltonian. So in this case, like you will see, you can write your time evolution of state again in some different form, but which is something the same one. So this is your the evolution operator, and this is your initial state. Uh, so this is psi t equals to 0. So and when you like evolve this, like when you operate the evolution operator, so you will see that like the evolution operator will act on the state phi n. So this will act on state phi n. So this will basically give uh, exponential of minus I e n over h. So this is the state, like I mean, uh, or basically like this is the evolution operator, you can say, like uh, I mean after when it acts on phi n. I mean, I think you know this event. We have done this over and over again in last uh, sessions. So when this acts on uh, phi n, so this will basically give you uh, So this will basically give you I P and H R T I. So which you know already. So so this is what happens in Schrodinger picture. So your psi t, you evolve with a evolution operator which we call it as US, that is exponential of minus I h naught over s per t. So that is the Schrodinger picture which you are very familiar with, or you often start understanding quantum mechanics with this picture. And what happens if what happens when you try to see the dynamics of quantum systems using different notion, that is Heisenberg picture. So in Heisenberg picture, uh, you evolve operators. So this is the catch right here. In Schrodinger picture, you evolve your states, your state of the systems that you are having a Hamiltonian corresponding to a particular Hamiltonian. You are having some state of the system which you are denoting with some vector that get a psi. So you are basically evolving them in Schrodinger picture. But what happens in Heisenberg picture, you are basically evolving your operators. So whichever operator you are interested in, like Hamiltonian, momentum, all these operators, you basically evolve them in time. So in Heisenberg picture, that is the case right here. So what happens, like how you see this evolution? Let's say this AS is a Schrodinger operator, and when you when you write this Schrodinger operator, like we write operator in terms of some matrices. So this operator can be written as some kind of matrices, this AS operator. So it will have the entries right here, some depending upon the size of uh, this operator, like depending upon the size of matrix, you will have that number of entries. I mean, and this entries also, which we call it as matrix amplitudes. So for a given row and column, so we know we denote row by I and column with J. So for uh, let's say we are denoting row and column with some alpha beta. So alpha beta denotes some row and column. So in that case, like we write the amplitude as uh, we write some alpha t, because alpha t denotes at some time we are writing this matrix amplitudes or the matrix as this thing. And so I hope like even this thing, like you know this, like which you had done this previously in many cases. So uh, yeah, so this is how you write matrix amplitude. So this is the matrix amplitude I have written right here. So I can write, like re-express this matrix amplitude like by changing the state right here, or like writing the state this I mean alpha of t and beta of t as some evolution operator ut0 beta 0, and this one right here is this thing, like where this is dagger. So yeah, and you will see that like I can comparing I mean I can call this entire operator right here, which is sandwiched between alpha 0 and beta 0, as the Heisenberg operator. So you can see that like this is basically you are evolving like the operators of Schrodinger picture, that A is with these evolution operators. So this is like how you evolve operators, and more explicitly you do this with this equation of motion. This is the equation of motion in the Heisenberg picture, where you evolve operators governing from this equation. So uh, and HS is also basically again the Hamiltonian in the Heisenberg picture, but you will find out like this is basically the same as uh, Schrodinger picture. The Hamiltonian has to remain same, and for example, if you do not have any particular explicit time dependence of this operator AH, so this term will go away. Like it will zero. It will basically just commutator of ah and hs when you take time derivative of your Heisenberg operator. But now, like in general, it can be non-zero.
Hello.
Yeah.
So physically, what is the significance of this Heisenberg picture? Because my state, say, any quantum state can evolve with time due to the
Uh,
effect of any Hamiltonian.
uh,
But if you want to know about the time dependence of the operator,
uh,
so what extra information can it give us
time dependent. I mean,
from the Heisenberg picture?
uh,
Why I need to? What is the physical significance of this?
I mean, physical significance, like there are no. Like it can be like, for example, let's say, I mean, in Schrodinger picture, what happens, like we are only like we want to know the dynamics of states. So like how states are evolving from those states, we are basically
Yes,
calculating some probabilities and all these things. But
yes.
like in Heisenberg picture, like we are only bothered about what is the operators, like on operators, like what would be the like particular value of operator after some time t. So in that case, like it may not be right idea to stick to the Schrodinger picture, because Schrodinger picture we only evolve states,
So
state where operator remains constant throughout the time. And
okay, so here in Heisenberg picture, the
mm,
uh, wave function will not change.
wave from like
The
wait,
state
wait,
vector will not
yes,
change.
yeah, in Heisenberg picture state vector will remain same.
Will remain same.
uh, I mean, because we express, like you will see in let's say, I mean, in Heisenberg picture we write the states as let's say, I mean, like I mean, yeah, some psi h, let's say, as uh, e I h, it's psi s. So psi is the Schrodinger state. So now, like when I say psi h, like uh, yeah, I can further write this as I h d h bar and minus I h d h bar psi s, that is t equals to 0. So that is basically psi h which you initially had.
Okay.
So this is by construction, like you have this.
Mhm. Okay.
So like if we are interested about like operators, we want to know exactly what the state of operator, I mean, what
So,
would how
for
operator.
example, say
Yeah. Yes, you can. I think I lost your voice. Are you speaking, are you here?
hello, hello.
Yeah, like I think I lost your voice somewhere, so
Oh,
you can tell me again. Yeah, again, I think there's some issue with your network. uh,
okay. Sorry.
yeah, now it is
So,
clear, you can tell me.
yes, clear. So, for example, at time t equal to 0, you have some state vector psi 1.
Mhm.
And I want to know after t equals to some time interval, uh, during this time your operator is changing with time,
Mhm.
but after some time your state vector will remain the same
uh,
according to this picture, Heisenberg.
like yeah, because I mean, we are defining like the state in this way, such
If
that
my question is, if the wave function doesn't change,
uh,
doesn't evolve, so what is the question of changing the variable dynamic the operator, the value of the operator? Because if the wave function changes,
uh,
then according to that there will be another value for the operator.
no, no,
Say
wave function like is always changing. Like the wave function picture, which we always see it through psi s. So,
yes,
but we are saying in the Heisenberg picture, the states that we are defining, because in Heisenberg picture, like let's say here in this operator h, like we are not like we are directly taking the derivative of h operator, and we are like calculating what is the like how it evolves through this evolution equation. But in Schrodinger picture, like we use expectation values, like if you remember, I mean, like,
Yes.
so this expectation is necessary, and for this expectation you also need to it is also necessary that like you need to have some particular state, because you will take the expectation in some state, some psi.
Yes.
So, but in Heisenberg picture, we are directly dealing with like this. I mean, operators. So in Schrodinger picture, the evolution would be something this thing, like you would have expectation, and the computation will also be will also have some expectation, and then further, like you will also have some del A over del T expectation. But in Heisenberg, you have only these operators, and we are defining such that the state in the Heisenberg picture would go like something this, such that like it would always be something psi h psi t zero. But you will see that like this in Schrodinger picture, this thing always tells you that like it is always evolving. Like, I mean, the state is evolving. I mean,
Mhm.
this is a different picture. Like the notion of wave function is something, or the state is nothing like Boxier and Heisenberg picture. I mean, there are no like you can think of like no like state notion or something. Explicitly for to calculate probabilities and all these things, we only stick to like the Schrodinger picture.
So here in Heisenberg picture, we don't need to think about the wave function because it
Yeah,
is it is not changing. Only the variation in the operator.
operators. Yeah,
Yes.
operators.
Okay. Okay.
Like when you think about like you cannot like mix this both the things. I mean, your state and operators, you cannot do that unless we go to interaction picture.
Okay.
That is what we will do in interaction picture. Because here both the interpretation will go through. Here separately, we will only separately like telling how operators will work out, and separately how wave function will evolve in that way. So yeah.
Okay. Thank you.
So yeah, like, okay, so for yeah, this is the Heisenberg and Schrodinger picture. But now, if we want to talk about like what happens in like interaction picture, like, and this is the interaction picture which you really need to uh, you have to adapt uh, to the problems or to the Hamiltonians which you have perturbation. I mean, or basically which you have time dependent in the Hamiltonian. I mean, like for time dependent Hamiltonian, you have to go to a interaction picture where the Hamiltonian is basically something like denoted as some H naught, the time independent part of Hamiltonian or the unperturbed part of Hamiltonian, and the time dependent part, which is HPT or the perturbed part of the Hamiltonian. So this is your time dependent Hamiltonian, and to again to evolve your state now, the state that we know in Schrodinger picture, we write some kind of this like evolution equation from Schrodinger equation, and you will see that like now our Hamiltonian is both time independent, time dependent part. So in that case, like you can see some state at some time t could be given by this Schrodinger equation. So yeah, and then I can further write this Schrodinger equation. Like you can see the state side as some evolution operator operating on the initial state, that is psi at t equals to zero, like on both sides of the equation. Then it's just so and then I can rewrite this equation back again is some I'm like basically I'm just bringing the right hand side to the left, and that is basically giving you this. So I h bar del us over del t. uh, minus h naught plus sp t us. So you, so you will see that like if this equation has to be true, then the equation which is in this third bracket, which is in this third bracket, or the this square parenthesis, so that has to go to zero. So that means this is one of the crucial equation. Like you have your evolution equation, like in terms of some us. I mean, you see, us is your evolution operator. So yeah. Sorry. So in this evolution of operator equation, so again, like instead of state psi, you have us. So this is your how your evolution operator is evolving. You think about now. In order to go to interaction picture, like we have to uh, talk about a different state which is given by let's say some chi of type chi of t. So this is, you will see that this is your interacting state. Like we will see like why this is, and we will evolve this state uh, with your free Hamiltonian like h naught or like I mean this is what this is expressed as psi of t, or otherwise you can write it as psi of t as exponential minus I h naught over h bar t chi of t. So to understand what is chi of t, we will again, what we'll do, we'll again put this in the Schrodinger equation. So how we started with this right here. So let's see like what would happen. I mean, so if we start again, then we have IH bar del t, then exponential minus I h naught is what t uh, chi uh, equal to h naught plus hp. So hp is your time dependent part of your Hamiltonian, and chi. So, so yeah. And so you do this derivative, like you will find out like you will have something h naught exponential um, yeah uh, uh, exponential I h naught over h bar t chi, then you have plus I h bar uh, exponential minus I h naught uh, over h bar uh, t del over del t chi. So yeah, and that is equal to h naught plus hp exponential minus h naught over h bar t chi. And you can see that like the first term right here, I can cancel this out with the first term, with the first contributing term of in RHS. So that will basically become this IH bar uh, exponential IH naught H bar T del over del T chi equal to HP exponential is IH naught H bar T chi. So here, right, you can think of like I mean, uh, so now you can do what, you can multiply exponential of minus h naught our h bar t from the left on both sides of your equation. So if I multiply my exponential of minus h naught over h bar t, so this will become basically equal to some identity operator. So your LHS will be this, and so similarly we will have on yeah. Sorry, so I think that this will be minus of so yeah. So you have to basically multiply plus exponential of plus I h naught or h bar on the left side. So you have to do the same on the RHS also. So this will give you this, and you have to be careful in this part, like the these things like when you are solving this operators, like here I'm easily writing this as identity operator because it was a trivial case, but let's say if you have some arbitrary exponential a and exponential b, like I cannot write exponential a plus b, like this is I cannot write that because I cannot write this because A and B do not commute with each other. Uh, or more precisely, you will see that like these are basically operators. So these operators earlier, like when we write like something exponential a plus exponential a times exponential b, it is some exponential a plus b if a and b are some numbers, like if a and ab are some numbers. But here they are not numbers here, they are operators, which means you have to expand each exponential a, like in terms of operator you have to expand it, and same for exponential of p, and then you will see that this entire relation is actually given by some Becker Campbell Hausdorff relation, or otherwise known as like BCS rule. So in BCS rule, you basically write, uh, I mean, exponential a exponential b equal to something exponential a plus b plus some half commutator of a b. Some relation is there. So it's a pretty big relation. You will see that like that is what we go with. But you can write I mean exponential of a and b as exponential of a plus b only if A, B commutes with each other. If they do not commute with each other, then like this is the relation which you have. So this is something you need to have. So that's why uh, you have to. You can see right here, like as I was writing, I was as I was writing this exponential of I h naught over h bar t, which I was multiplying it from the left side on both the sides of equation, like uh, like let's say for this one right here. So this one is multiplied. Like you can see that this is some operator a, and this is some operator b, and this is some operator c. So you have to be careful because you cannot suddenly interchange, you cannot multiply when I'm multiplying operator a on the left on both the sides of equation from the left side. That means I have to write a multiplied with b multiplied with c. That is how the operator works. You cannot write like b a c arbitrarily, because in left hand side I operated a from the left, so that's why this term was earlier there, and then when I operated with this thing, so it become identity, because here you can see here both h naught is there, so both the operators are same basically. So a commutes with a, so that's why I will have exponential of a plus b, which is basically zero. That is exponential of zero equal to I. So this some some technical information that you have to be careful about when you are working on operator basis. So in this operator basis, this is how this computation and this exponential works. So now, moving ahead with the interaction picture, so which I was telling. So this thing right here, which I have shown right here, which we call it as uh, H interaction, or otherwise the chi state which we introduced is basically is the step which evolves with interacting Hamiltonian, yeah, H in chi. So now you can understand the chi, that this is a state which evolves with the interacting Hamiltonian, unlike the free Hamiltonian, which we evolve it with for a Schrodinger state. But this is an interacting state, chi, which evolves with interacting Hamiltonian. So now you can check right here, this chi of t can be written as u interaction uh, chi of t0 kind of initially, uh, and also you like this chi of t0 is basically initially, as I defined right here. I should have written here, uh, the chi of t equal to 0 is basically equal to psi of t equal to 0. So yeah, so this is basically you are evolving your your normal side t equal to 0, because this is equal to same thing as chi equals to 0, with the evolution operator which encodes interacting Hamilton. So yeah, so then uh, so then basically again, if you would write like your Schrodinger equation as we earlier did, like you can write it as u interacting equal to H interactive, U interactive. So this is your evolution. I mean, this is your uh, uh, the governing equation for how your time evolution operator will work. I mean, how you can estimate your time evolution operator, like as we tried to see earlier. I mean, somewhere right here, uh, yeah, this one right. So this is how your evolution operator will be evolve to. Like if you try to solve what is the evolution operator from this equation, like you will get a very like a complicated expression from here for the solution of U interaction, because I mean this actually gives rise to Dyson series. Like if you do quantum field theory in future, like this is something the starting point you will see. Like I mean, basically it involves time evolved. I mean, time ordered evolution operators. Like this U interaction is otherwise something you will express it as in that time evolution operators. So like what happens, like if you try to solve this, like you start solving this with some ansatz where you take you interacting you take which your interaction is your solution in some orders, some epsilon, so that is your interaction 1 plus some your interaction uh, 2. This is basically epsilon square, uh, yeah, and so on this will go like so this so this new interaction, if you solve order by order, like you will like for order like epsilon to the power 0, like you, I mean, uh, you have this IH bar del t u uh, u 0 interaction. So that will that is 0, which is simply you can think of u yeah, u interaction 0 as some constant operator, some constant operator. So this constant operator is basically nothing but some C multiplied with some identity operator. So and same like you can think of like uh, for order one epsilon you will have something minus bar del t uh, one interaction as some like hold a minute like there's something at the door. Yeah, sorry for that. Yeah. So yeah, I was talking about like this how you can calculate the solution for this Dyson series. So yeah, for the order epsilon, you will have something um, H interaction on the RHS. So right, you interaction. This will be I think zero. So, so for here, your solution would be uh, you. Uh, so, like here, I think your solution would be u interaction one. Uh, okay. So yeah, u interaction uh, one of t is basically minus I over h bar is 0 to t dt prime and h interaction t prime. And same like if you write so if you write here like what, epsilon 2, so in that case you will have uh, uh, okay, so here you will have IH bar del interaction 2 del T H interaction, and here you will have new interaction 1. So so again in this case you will have new interaction 2 T uh, then we have some minus IH square 0 to T H interaction T prime and interaction T double prime dt prime. So yeah, so that is how it will go. So but you will see like this is given as some kind of like time ordered like some exponential uh, 0 to t prime t prime h interaction. So so this is how it is written. Like when you do like this, uh, what I mean, uh, your point of view theory that this is something this time order. So time order means like the integral which you will see here. So the integral which appears here. So like you have to be careful when you take like let's say your time goes as 0 to 1 t2 uh, T3 zone some T. So you have to like integrate like because this Dyson series involved will like in general it will want many multiple integrals. So here also there also involves some another like I mean when I am writing this U interaction uh, uh, T prime. So I mean this is basically uh, um, like uh, wait a minute something I think I missed here. Uh, yeah, like this U interaction, this is basically U1, and that is like which is written right here. So U1 again contains this integral. So So this u1 you can see like two integrals are coming in the same u integral to uh, express it. So that's why like you have to be careful like, which time you have to integrate. So if you are 0 to t, then it would have some t prime, and t prime like should fall between like 0 to t, something like I mean you would see explicitly like where when you will do the I mean this in quantum field theory like you will. But for now like we won't be like using this explicit time order thing in this case. So like even the problem which we will discuss, so there you will have some straightforward like computation which you will see. So it's mainly you should know that I mean your I it's del by del t, your interacting state is I h bar h naught t h p t I h naught t. So this is your h interaction chi basically I h bar del t chi h interaction chi. So yeah. So this is the idea about interacting picture. So I hope like is there any doubt or any problem in interaction picture?
Okay.
Fine.
Yes, yes.
Okay. So like this is the like the question we have solved it before also. Like, we can like quickly go through. So so suppose like we have a spin-off particle in a time-dependent magnetic field. So and that magnetic field is given by this. This is the time-dependent magnetic field. So in this case, you have to calculate what is your Hamiltonian. So again, like we will try to express our Hamiltonian in terms of some like unperturbed or perturbed part. So and after when we have the Hamiltonian in this form, then we can decide like what would be the interacting Hamiltonian. But just for like for the case one, like where it is only asked what is the Hamiltonian, like, we just simply have to construct the Hamiltonian. So that Hamiltonian can be calculated by this. Like if you have a spin, any spin particle in a magnetic field, so this is the Hamiltonian. This is the how you write the magnetic field energy or magnetic energy. Because I think you are familiar with this idea of magnetic moment, or like from electromagnetic course also you would have seen this, like if a magnetic dipole moment or a magnetic moment is kept in a magnetic field, so the energy is this minus mu dot b. So that is the dot product of magnetic dipole moment which is kept in the magnetic field with the magnetic field strength, that is b. So you take the dot product, and this magnetic moment is again like expressed as some minus gamma s, where uh, like gamma is some like I think uh, something related with gyromagnetic ratio, and this is like or like I think like this mu is basically it is, if you calculate like it would come out to something eh bar 2, I mean eh bar 2 and something like I'm not sure, I mean I do not remember. Like this is something would come out as some core magnetic. So so yeah, that is like some details that uh, I think you are already familiar with, because this is a thing which we do in electromagnetic like problems. I think yeah, you would see in other places as well. So yeah, so then this gamma is written as magnetic moment, and that means you have to take the dot product with S and B. So, and your spin is like written as some vector that is each of this component is given by this, and you are doing the dot product with your external magnetic field, which is time dependent. So, and again, you're writing your spin as we also discussed before, like today in this session in the beginning. So, where we write Sx operator as in terms of Pauli operators sigma x. So, and same as sigma y, sigma c. So these are Pauli matrices, and these are how the Pauli matrices are written. And if you substitute this like in place of Sx, Xy, and Sg, so this is what you will have, um, minus gamma b naught h bar. That is the factor which taken out, and so this is the result of dot product sin theta cos omega t is sigma x, and sin theta sin omega t is sigma y. And substitute what is sigma x. This is your sigma x like from here, sigma y from here, and sigma z. This sigma z is from here. So solve them, you will get this final matrix form of your Hamiltonian. So which is time dependent, and this you can further split into, you do some rearrangement here, like you can express this cos omega t minus sin omega t, I sin omega t in terms of Euler relation. This is exponential of I minus I omega t, and same with this element also. And then you have the complete matrix form of your Hamiltonian, which is time dependent. And then you can see what you can split this Hamiltonian as diagonal part and off diagonal part. So this H0 is your diagonal part. So we always write, because your free Hamiltonian always stays in a diagonal basis. So that's why like you can like split this Hamiltonian into a diagonal part, and this is a off diagonal part, which is your uh, which is this is basically your HP, which is your time dependent part of your Hamiltonian. This is the upper term part, and then yeah, so and this e1 and e2 are given by this expression. The e1 e2 are basically uh, same uh, in magnitude. They only differ by the sign. And then you have your Hamiltonian finally. So that is the first part of the question. So and then suppose if the state of system is governed as this thing. So this is a brief description like I have given here, like, for the interacting Hamiltonian. Uh, so basically what it is asked, like you have to determine a chi. So you have to determine what is interacting state with the help of interacting Hamiltonian. So we have the total Hamiltonian right now. We have the free part and also the button part. With that, we can construct what is our interacting Hamiltonian. So with that interacting Hamiltonian, we can determine what is chi. So and chi at t equals to 0 is given to be upstate, the spin upstate. That is this upstate in SZ basis. So so this description also I was discussing like that day. So like I mean like and I think we have covered this discussion again here. So I think like what interacting Hamiltonian are and what interacting states are. This is basically the final thing which you have to know. Yeah, this is your governing equation, and from this like you have. Uh, uh, yeah, like here I'm showing that like in your I mean you can write this Hamiltonian. I mean like if you let's see here, exponential of minus I over h bar h naught t, because for interacting Hamiltonian we have to calculate this hpt sandwich between these two evolution of these two of u operators, exponential of I h per h naught. So this is unperturbed. Remember this is unperturbed and this is perturbed. So again, so between these two operators, this HPT is sandwiched. So that means like you have to like because we have perturbed Hamiltonian in some matrix form. So we are trying to construct this exponential Hamiltonian also in some matrix form. That is by this way we are expanding this exponential operator order by order, and then we will see like uh, this H naught uh, uh, Yeah, so we are expanding this Hamilton in this order by order, and like if this uh, uh, Hamiltonian acts on a state, then it will basically give out like this energies, like E1, the eigenstates. So because we have like two eigenstates right here, so that would correspond to E1 and minus E1. So so this is what it is written as. So exponential of minus I over h bar h naught as this matrix form, and then yeah, and then you have chi some C1 C2 state, and when you evolve it with this operator, it will give you some psi D1 D2. So like this is the part like which we introduced in during our discussion, how interacting Hamiltonian or I mean how interacting states chi is related with your Schrodinger state. So this is how it is related. So so then if you would calculate, so we have all the information right now, because you'll see that like your D1 D2 are this. Yeah, then uh, in this you will start from this equation again. So your H interaction is basically this, because you got the matrix form for this and you already have the matrix form for H perturbation already from the first question. So you will get the H interaction. So you have H interaction, that is this matrix form. And so yeah, then you solve this equation, you will get some differential equation, and this differential equation you will get two differential equations which are coupled. To decouple them, like you will I think that we have discussed very well. So you can also check out the recording video there, like, for the detailed discussion. Like right now we are falling short of time, so maybe we can uh, like we can, that's the last we can discuss right here. So but like we have discussed it, like how this differential equations can be solved, like this is basically a couple differential equation. First you have to decouple them, and like that is, I think I have given this equation, like how to solve, like I mean how by taking that one more derivative you can decouple, like this is how you can see where this is only, this is a differential equation only in terms of C1. So this is what you will get after decoupling. So again we'll have for C2 also, and solving these two equations, like you will get some yeah, you can get a solution like this, you t C2 of t, and after you have C2t, then you can also calculate what is C1. So and initial condition, like where C1 like is this C1 C2, like it is already given to us in the question, that is it was initially upstate. So that information I am putting right here, this is right here, and from there like you can calculate what is chi of t, that is because from this information in the initial state, which is 1 0, you can calculate the arbitrary constants, that is I think a plus and a minus, and from there you have C2t. So yeah, that was the question about how to calculate using the interactive Hamiltonian. So so I think like this is clear now, like because this was a bit long calculations like involved in it, so it would take more time. I think I have also discussed this again. I mean,
Yes,
very well I think in week 4. You can check out
yes,
the
yes,
notes or also video today.
yes, yes.
So and yeah, like as you were telling about many other things, like
No, it's okay because
yeah,
time is really short.
yeah, yeah,
It's,
yeah. I mean,
so
hopefully,
can you? Yes,
yeah,
yes. Okay.
yeah, yeah.
So okay, I just want to know because can you please tell me if I want to study quantum field theory, then what will be the
Uh,
precondition? What kind of course I have to take?